So we're going to talk a little bit about a mixture problem. What we want to do is we're going to suppose that we have a chemical in a liquid solution. It could also be dispersed in gas, which runs into a container holding the liquid or gas with possibly a specified amount of the chemical dissolved as well. The mixture is always going to be considered uniform because it's kept uniform by stirring, and it flows out of the container at a known rate. In this process, it's often important to know the concentration of the chemical in the container at any given time. So we have a solution of some percentage salt, and we're pouring it into a container which holds a solution which has maybe a different percentage of salt. And as it pours in, that mixture is changing. The percentage changes depending on how much we pour in. So that's kind of what we're thinking about here. And we can set this mixture problem up using a differential equation. And so when we set this differential equation up, we have a rate of change, a derivative, of the amount in the container is equal to the rate of change at which the chemical is entering the container minus a rate of change at which the chemical is leaving the container. If we consider some function y in terms of t to be the amount of chemical in the container at time t, and this function v of t is the total volume of the liquid in the container at the time t, then we can calculate the departure rate of the chemical at any time t by saying the departure rate is the amount of the chemical, y, divided by the volume of the liquid in the container, multiplied by the rate at which it is flowing out. And so y of t over v of t, that is going to tell us the concentration in the container at time t. So accordingly, we can take equation 6 up above, and we can say the derivative of y with respect to t equals the rate at which we're going into the container minus whatever that concentration is times the rate at which it's flowing out the container. So if y is measured in pounds and the volume is measured in gallons, t being measured in minutes, we could say pounds per minute equals the pounds per minute that we are going in minus the concentration, pounds per gallon, minus the gallons per minute that it's flowing out. So it's just a way of thinking about setting up that equation. So now that we understand the setup, let's jump into an example. So we'll read through our problem here first. We're going to do a salt mixture problem. A tank initially contains 100 gallons of brine in which 50 pounds of salt are dissolved. A brine containing 2 pounds per gallon of salt runs into the tank at the rate of 5 gallons per minute. The mixture is kept uniform by stirring and then has an outflow rate. It flows out of the tank at a rate of 4 gallons per minute. So part A here says, at what rate does the salt enter the tank at time t? And when we talk about that rate, the rate that it's entering the tank is going to be in pounds per minute. So A, our rate entering, is going to equal the 2 pounds per gallon times 5 gallons per minute. And what that gives us is that my rate is 10 pounds per minute. So that's the rate that the salt is entering the tank. So part B says, what is the volume of the brine in the tank at time t? And the way we're going to do this for B is we are going to say, I'm actually going to give myself some more space and write this down here. B, we have V of t equals 100 gallons plus 5t gallons minus 4t gallons. So what we have here is the initial brine plus the rate at which it's entering minus the rate at which it's exiting. And I can simplify this because what I end up with is V of t equals 100 plus that 5t take away 4t is 1t. So I have 100 plus t is my volume function in terms of t. Part C, at what rate in pounds per minute does the salt leave the tank at time t? So the volume at time t, we know, is that V of t is 100 plus t. And the salt in the tank at time t is Y pounds. So the concentration at any time t is Y over 100 plus t. So what we can say then is the rate at which we are leaving so that rate leaving is going to equal the concentration times that outflow rate. And my concentration is Y over 100 plus t. My outflow rate is 4. So my concentration is pounds per gallon, and my rate is gallons per minute. So that gives me that my rate leaving is 4y over 100 plus t, and that would be in pounds per minute. Okay, so we had the concentration there, and the concentration is pounds per gallon times that rate, which is gallons per minute, which leaves us the gallons cancel, and we end up with pounds per minute. So that is my rate at which I'm leaving. So I'm going to skip to the next page and bring that problem back in. We have 2 more parts left to consider here, D and E. So for D, we're going to write down and solve the initial value problem, which describes the mixing process. And so thinking about this for D, that total rate is going to be the rate that it enters minus the rate that it exits, or that it leaves. So we can say dy dt, the rate at which we were entering was 10, and the rate at which we are exiting is 4y over 100 plus t. So here we have a differential equation, and we need to get it into our standard form so we can determine P and Q, and we can solve the equation. So I'll subtract that 4y term, or I'll add it to the other side, and I have dy dt plus 4 over 100 plus ty equals 10. So my P equation is 4 over 100 plus T, and Q is 10. I need to find my integral of P because that goes in the exponent of Euler's number E, which gives me my integrating factor. So the integral of P is the integral. We can pull that 4 out in front. So I'll say 4 integral 1 over 100 plus T dt. And that integral is the natural log of 100 plus T. Technically absolute value bars, but because we're dealing with time, which has to be positive, we can drop those. And I can take it one step further and say that's the natural log of 100 plus T to the 4th power. So V of T, I'll actually do that in another color. I'll do it up here. V of T, remember it's e to the integral of P. So e to the integral of P, that's going to be e to the natural log of 100 plus T to the 4th. V of T is just going to be 100 plus T to the 4th. Okay, so we find out that V of T is 100 plus T to the 4th. And when I multiply by my integrating factor, I know I'm going to get the product of V and Y on the left. And just a refresher from previous section, one thing that we already know is that we're going to end up with V of X, Y equals the integral of V of X, Q of X, dx. So that's what we know, and that's why we talked about how we can pick this integrating factor so that the left side of my equation simplifies down to Vy. So we already proved why this would happen in a previous example. So I'm going to take this, what we know here, and rewrite it. I can divide by V and I'll get 1 over that V of X is the integral of V of X, Q of X, dx. So setting this up, I now know that Y is 1 over V, 100 plus T, quantity to the 4th, times the integral of Q times V, which is 10 times 100 plus T to the 4th dt. And the integration that we're looking at now is fairly simple. I'm going to take that 10 and pull it out. I've got y equals 10 over 100 plus T to the 4th. The integral then of 100 plus T to the 4th dt. And that is easy for us to integrate using a u substitution. And we end up with 1/5 100 plus T to the 5th plus C. So, of course, we can distribute through here. I've got y, the 10 and the 5, 10 times 1/5, I've got 2. And then 4 of those are going to go into that and just leave me with 1. So I've got 2 times 100 plus T plus 10C over 100 plus T to the 4th. So whenever something has a variable in it, again, when we're doing these differential equations, we have to distribute. And because we were given an initial value and we were told that we started initially at t equals 0 with 50 pounds of salt in the tank, we can determine exactly what C is. So I can come over here and say, for my initial value part of the problem, 50 equals 2, plug in 0 for, for t, I just get 100, plus 10 c over, again, I would have 100 to the 4th. And we'll do a little bit of magic algebra and determine here that c equals negative 150 times 10 to the 7th. So if I know my c value, then my solution here is going to be y equals 2, 100 plus t minus 150 times 10 to the 8th over 100 plus t to the 4th. And so part E says just find the concentration of salt in the tank after, or 25 minutes after, the process starts. And so part E is pretty simple for us to calculate. Part E is just plugging 25 in. So for part E, we need to find y of 25, which is going to equal 2 times 100 plus 25, 125, minus 150 times 10 to the 8th over 100 plus 25 to the 4th, which, plugging into our calculator, gives us 188.56. And then in order to fully find the concentration, we need to take that 188.56 and divide it by the amount of brine in the tank, which is 125. So my final answer for my concentration after 25 minutes is approximately 1.5 pounds per gallon.